Currently, most of the post-training of large language models are done via reinforcement learning in a centralized cluster of GPUs. This cluster is doing a lot. You need to take care of fine-tuning the model weight, but also you need to maintain an environment, generate rollouts, score them, and keep the inference models up to date so that the training and inference doesn't diverge too much. Interestingly, about 80% of the wall clock time is spent on rollout generation, which are kind of simple in the sense that they are inference-only forward passes. This means that quite a lot of compute time is wasted. In this video, I'm going to present you a method to better use centralized data center GPU for post-training by offloading these rollout generation to a distributed fleet of workers all across the world. This method was developed by Gradient, which is the same company that built Parallax, who are kindly sponsoring this video. The core system is called Echo and it was iteratively developed in late 2025 with Echo 1 and early 2026 with Echo 2. In the most recent version, we have one swarm made up of consumer GPUs, which are running the parallax inference engine and handle the rollout generation. The other swarm is sitting on data center GPUs, all centralized, and handle policy optimization. The ecosystem get very similar results in performance than the fully centralized training run with lower cost since the rollout generation doesn't need to use data center grade GPUs. For instance, they brought the cost of post-training a 30B Quen model from around 4.5K down to $425, which is a significant 10x reduction. In the first half of this video, I'm going to walk you through the Echo framework and the results. And in the second half, we will sit down with Eric Yang, one of the co-founders of Gradient, to dig into some of the engineering decision behind the system and where the Gradient distributed training stack is heading next. Enjoy! Okay, so if we look at the Echo framework, there's actually two papers related to that. One from late 2025 in August, another one just after that in 26, and they're kind of a continuation of the same thing. In the first Echo, the main focus was on checking if splitting the inference and then the training was viable and then as good as having everything in the same stuff. So the idea here was to use the two phases in consumer grade GPUs and see if we can make training these model, the Quen's family, from 4B to 32B match the collocated Verl baseline. So you have these, you have the sequential mechanism that they had and the asynchronous mechanism. I'm gonna explain this in a second. The sequential mechanism is kind of like this asynchronous. It's just that it's waiting. The training system will give it a new version of the model before continuing. The asynchronous kind of doesn't care and will continue producing rollouts. And you have these three elements. We have the inference swarm, which is a pool of GPU just for inference. And here it's using the parallax engine that we discussed previously. So it's one big model that is split up into different GPUs. You have the training swarm, which is collocated onto a single thing. And then you have what they call the model snapshot buffer, which is kind of looking at all of this. In the asynchronous version, you also have the rollout buffer and the coordinator for all of this stuff, but they're kind of doing the same type of work here. All of the result was with the sequential mechanism, however. And then you have the Echo 2 version of it, which is pushing Echo 1 a bit to the extreme. Echo 2 actually is taking this part that was kind of under discussed in the paper and then just pushing the off policy RL type of a situation to the maximum. So here you have three phases. You have the learning plane, you have the data plane, and then the rollout plane, which is kind of the same as here, right? But in a much more specialized way. The learning is centralized, so it's on a one centralized cluster. So we're not doing you're gonna train and inference on a big pool of distributed GPUs that all are running at the same time. The learning is happening on a centralized bunch of GPUs, but the rollout generation, the one that is 80% of the wall clock time and most of the cost, is being taken care of in a decentralized wide area network here. See here we have all of the different workers, they're kind of connected in a certain way. I'm going to talk about that. And then you have a system that is kind of an orchestrator, a bit like this over here. And in this system, it's not just one or two steps behind that you can be up to 11 steps behind. And then this system will kind of coordinate and figure out if a rollout is useful or not and legal or not for the training of the learner. So there's a whole bunch of stuff. This setup is a bit more complicated, but we'll see. We're going to go step by step on it. So with Echo 1, we're going to look mainly at the sequential mechanism, the setup. Basically, it's the same thing as a collocated reinforcement learning setting. It's just that you are gonna split the concern, and you have one pool of GPU that is doing like the inference type of stuff to generate the rollout, and then you have another bunch of GPUs that will just do the training. And then this will be APIfied, so this one will call the inference swarm to get rollout. You're gonna return the response over here. This one will check the model version to see if like you need to pull the model weight, and this guy, the training swarm, will push the model weight here, and it will just wait if need be. So we're always pushing the model weights as it train their parameters, and at the end, like, you will return the response, and you just iterate like that, right? And this is optimized as much as possible. Asynchronous mechanism is like Echo 2. So if we look at the performance here, right, you had 3 tasks, which were pretty interesting. You have the Sokol band environment, which is kind of a puzzle thing. You have another puzzle here, the KNK puzzle with the 32B. Here, this one was a 4B. And then you had like a math type of a verifiable reward task with like a 7B model. And the performance is good. Like the Echo with GRPO is like 34% success rate here, and as you go bigger it gets better. So like overall, like this is pretty good. So here for the math, the Echo 7B, the GRPO is actually like being better than like the 7B baseline and 32B baseline. So it actually is learning something. And same thing here for the KNK. This is actually a pretty easy task for all of these models, but it's doing great. And if you look at the like just the Verl one, so like all collocated, and the Echo one, it tracks, like it's actually doing the same thing in both. And like I said here, it's a sequential mechanism that is more accuracy centric that has been tested. So at each inference step, the model is synchronized during the rollout generation. So this was mainly a proof of concept that like you could separate these two, and then like you can use like a pool of consumer grade GPU to do the inferencing, and it worked pretty well. Now, the asynchronous portion, in my view, was the most interesting part of this paper, but I didn't do the benchmarking and test because I think like they figured out it was a bit difficult to wrangle properly, and then they just literally pushed it to the maximum, and then you get like the really cool Echo 2 version. So now with this, you have the inference swarm over here that is doing the same thing of like pulling the weight from the model snapshot buffer. And then you have the training that will kind of pull the rollout. So like it's not calling the API and then getting something in return. It will just continuously pull the rollout and then like get the model version number. And here, this is where like if they're too stale or whatnot, you can like kind of cut it out and don't push this rollout on the training swarm. And then once it's trained, it's gonna push the model weight like at a cadence whenever necessary, and then this guy can pull again and then push the rollout. So you have the push-pull system over here. Keep that in mind because this is what's happening in Echo 2. In Echo 2, this is the same kind of learner. This is just a centralized learning system. And then these are kind of the worker that are just like generating rollout. Their sole purposes is to generate the rollout. They're also going to do their own reward scoring, and then they're going to push that to the replay buffer, right? And then they're going to tag at each point in time which model they use to do that. At some point, like the learner will publish a new policy, right? And then these guys will take it and then they will use that now. And if you see here, it's not pushing it to everything, it's pushing it to the first one. And there's kind of a tree structure to kind of broadcast this like policy to all the other ones. So these ones are kind of in a kind of latest structure. So that's kind of that. And then like there's kind of a system to filter some of the rollouts. So these are continuously like generating rollouts. They don't care about what's happening. As soon as there's a new policy, they take it and then they update their stuff. So the proper filtering of the rollout is taken care by the replay buffer. There's some stuff about the task here, but it doesn't matter too much. And then here, there's a cost-aware provisioning, right? So that like, depending on like how many GPU are available in the system, you can increase the number of worker or like reduce them and allocate them into different pools. That's the idea. And like in literature, the one thing that is coming close to this type of system is really the Intellect 2 system from Parametellect. But in their case, it was all fully decentralized. You had the inference worker, you had the GRPO training worker, you have the top block validator, and then like they were all kind of, these clusters were kind of all interacting in parallel. Where a gradient with the Echo 2 look more like it is this decentralized two-step asynchronous training, right? It's actually more than two-step, it's S steps. So it's not like all synchronized at the same time. The Echo 2 favor some off-policy reinforcement learning for optimal efficiency. In practice, how it looked like is that you have learner at the top, right? So here you have the different version of the learner. You have the V0 up to like V6 over here. And then you have the replay buffer that is giving to the learner like the different rollout that it can use to train. And here you have the rollout plane where you have the worker that are generating the rollouts, right? So here you see up from here to here, you have only V0s, right? So even though the learner went from V0 to V1 and V1 to V2, this one is still using V0's rollout, right? And then like at this point, it get broadcast that like, hey, V2 is now out, we should change. So at this point in time, this one is still V0, but then it switched to V2, right? It does never touch V1. And then at this point, like it will generate V0 rollout. Now we start to also generate V2 rollout. And here, while this was ongoing, right, the V2 went to V3 and V3 went to V4. And then like we continue as is here. And you see some of the filtering is happening. We still had some V0 rollout from before, but we didn't use them because like it's getting too stale now. So we're just gonna prioritize the V2 and then the V2 here and then the V4. And it just continue in time again and again. So this is actually a good visualization of what's going on. It's very dynamic, right? But this is a good visualization. So if we go step by step, right? So the main thing about Echo 2 is that like you have now a budget, right? You have like a staleness budget S, which your person that is kind of training their system is saying like up to S, I'm good. Like I'm good to have like a policy staleness of like 6 step with my worker. So my worker can be doing inference, right? With the 6 step behind policy and it will still work out great. I'm willing to have that. And then these rollout can still be used. And the system, what he will do is he will try its very best to always have the rollout coming from model version 6 or below, right? So if it's 0 and you have a policy budget of 6, they will still use these, right? And if it's 7, then you will start to discard them so that it doesn't infringe on this. There's a bunch of stuff that it will take into consideration in order to decide like how it's going to optimize the system. One of it is like the effective rollout throughput, right? Depending on like the GPUs that you're able to provision and the monetary cost per unit of time for like these GPUs. This will be calculated with like the ratio of these two. So here we're talking about like the learning plane at the top and the rollout plane. And then depending on your budget that you're set up, this will dictate like what type of worker you're gonna get and what type of rollout you're gonna be ingesting in your training. So based on these numbers, then you're able to kind of figure out kind of like a kappa, right? That will tell you which frequency you should be updating these models, right? Because technically, like if your S is very big, you don't have to update the model too much. So the throughput of the worker will be very high, right? And you can use very cheap ones because like you don't need this thing to be fast and very insane, right? So it will cost you a lot less dollars in order to post-train your model. Quality of the training, like as you go away off policy, start to be a bit brittle, but that's kind of the trade-off. So the user, depending on their task and like whatever they're training on, can decide what type of off policy they would want. With all of this, you get like a kappa, which tells you like which is the frequency that you're gonna update, right? And before we had a kappa of 2, because you see here we have learner, and then we waited 2 before we broadcast, again 2 before we broadcast. So you're not always broadcasting. So you're saving some bandwidth because like these model could get pretty big. Then what you have is like the provisioning, right? So like how much of these, like based on like the information above, right? You're gonna be able to decide how much of these you need, and you're gonna put them into like a kind of a tree structure so that they can update each other. And that's kind of that. Like so, you'll be able to look at like their cost and like their performance, and you're gonna be able to kind of provision them for this user to run their training run. And lastly, it's like the same thing as like we saw with parallax, right? Like so this is supposed to be in a dynamic system because Gradient want to be able to kind of create this sort of lab with like distributed pool that you can kind of put your GPUs on. So there's a dynamic aspect to it. So like depending on like what's going on here, right? You have all of these workers that are like reporting some stats, exactly like the table that we saw with parallax. And they're reporting the stats, and there's a provisioning kind of layer that is looking at this. And then if like a worker is kind of being a straggler, you will be able to swap it out. And if like you need more, you will be able to add it in. And if you need less because like the thing is going pretty well for your task and you actually need less provisioning that needed, you're gonna remove like the most costly one, and then you'll be able to save dollars here. And lastly, like the peer-to-peer broadcast system is pretty interesting because instead of having like the main learner or like the main orchestrator push the model weights to everyone, right, at the same time, what it will actually do is like it will push it to one and then stream it to this worker, and the worker will be able to kind of stream it to its peer, right? So we like this peer-to-peer kind of broadcasting system existed forever in like different scenario, but now we are able to use it to save some bandwidth here and to speed up the time for the propagation of the new model weights. So this is why like these worker are kind of peer-to-peer connected. And that's kind of that, right? So a lot of stuff is happening over here, but those are the main point. So if we look at the whole flow again, you have the learner. It's like trying to learn with gRPO, and it's like ingesting a bunch of batch of rollout, right? And then like once it has a new policy, it will update them to the worker. The worker will start to like switch it up and then like put the other type of rollout with the new version on here. And then if for some reason, right, network connectivity issue or like whatever the heck, the rollout is longer, the rollout start to become stale depending on your budget, it will filter them out and then you're not going to use them for learning. And then while you're doing all of this, there's like a provisioner layer that will decide if you want to add more to the system or not. And when the policy is updated, each of the worker is kind of acting in a latest structure in order to broadcast the weight to the other worker. If we look at the performance, it's pretty simple. Like it just worked. So that's the thing. So here you have the reward mean value for Amy 24, and there's a lot going on here because like there's this axis and then this axis. But basically, the Echo 2 and Echo 2 with the policy staleness of 3 and 4 are kind of like doing the same thing at the end, like the Virl sync baseline, and there's also the Virl async, but like collocated. It's doing kind of the same thing. However, it's cheaper, right? So as the training step increase, the cost is like at a different slope than the other two that are more a centralized system. If we look at the effect of bounded staleness, it's very interesting because this depends a lot on the task and like on many things, right? But you, like the user, decide like how much staleness you want. And if you take too much staleness, right, it should cost you less. But what happened is at some point, you might collapse the whole training. So let's say here has staleness of 11, right? The workers are 11 steps behind the trainer. It starts to just break down. Versus like 6, 4, 3, like you still get like some good performance. So there's like a budget here that you can allocate depending on like what your task require here. This is very interesting to me because I was reading this other paper. LLM can learn to reason via off-policy RL. And in their case, like the guys from Databricks, they developed another algorithm called OIPL, and their algorithm was able to go to up to 400 steps behind, which is kind of crazy. So like in the case of Echo, they were using gRPO, which has trouble with like off-policy setting, but OAPL is a bit better. So there's also like tricks that you can use. You can use any algorithm here to train your stuff, right? So you don't, it's like algorithm agnostic. So you can try other type of training algorithm for the reinforcement learning and try to test out like the different S that you can use and see if you can get still no degradation. They also checked out like, because this is a trade-off between like using all of your rollout as much as possible so that the learner is saturated and just failing the run completely. So there's a bit of a gamble here. And then they tested with different number of workers, right? And different number of staleness, what you get. And with like 6, 5 workers, you can go up to 6 and 4, and then you're not gonna get like much bubble here, right? The least amount of staleness you have, the more worker you need. So there's also like some ratio that you have to figure out depending on your task here. And that's kind of that. So let's now talk to Eric Yang, the co-founder of Gradient, and let's ask him a bunch of questions. Well, first of all, thank you, Eric. Thank you, Eric, for coming here. Can you talk to us a bit about yourself, what you're working at Gradient right now, and like your background?
Yeah, so thank you, I think, for having me. So my name is Eric. I used to be a Berkeley graduate back in 2013 to 2017. I studied computer science at Berkeley, and later I become one of the founding engineers in one of the Silicon Valley startups. We operate the live streaming content platform business for like 2.5 years. We raised around like $15 million back then, and then we at that point we got few million monthly active users. We signed PewDiePie to do exclusive live stream on the platform. And in 2019, the company got acquired. And after that, I was asking myself, what do I want to do next? So back when I was still an engineer, I always feel like I want to kind of get a more holistic view of the commercial world. I'm deeply curious about how human society and also like the business world as a whole operates. So I want to jump outside of my comfort zone. So that's why I start my career as a venture capitalist. I joined Sequoia Capital China to be one of the investors there. Actually, I was the one of the youngest investors that was working in Sequoia Capital China, and we invested in a whole bunch of different areas. We invest in B2B SaaS, we invest in game and metaverse, we invest in crypto, and there are like at that time I covered most of the software related business. And in 2023, I also started to look at generative AI. After like around like 3 years of being an investor full time, I started to think about I actually got like the time has come. Like the time for me to actually to do something on my own has come, and
Yeah.
I'm super prepared for this generation. And I think like as a young people who haven't got the chance to make some waves in the consumer internet phase, the generative AI phase are definitely one of the bigger waves here. So I want to grab this opportunity to become someone who make a difference for the world, who can build something that was actually meaningful to the world. So that's why when I then come out of Sequoia Capital China to start a Gradient. It's around later 2024, and we have been running Gradient for like more than 1 year as of right now.
So it's really cool, and I'm gonna ask this because I'm actually curious. What are the top thing that you brought from your work as a venture capitalist that like kind of reframe how you were thinking about it? Because you were like founding engineer before, and now you went like all the way to the venture capitalist side, which is gonna usually the other side of a startup. What was the top thing that that changed a bit your worldview here?
I think I think it's more like so when you operate as a founding engineer, you're looking at every line of code in a very detailed level. You look at the specific detail of how things work, right? And fundamentally, as an engineer, I think we both share the view that we need to get to the very bottom of it to make sure
Yeah.
it works, not having any bugs. But as a venture capitalist, it sort of trained your way of thinking, of generalize the world, of looking at things more like fundamental, like, or even sometimes, look at things in a very long horizon way. For example, like back then when I was a software engineer, I don't know how like great business was invested. Like, what are some of the like ups and downs for those businesses, and what ultimately was the key success factor of that business. We don't actually get to know those details. But when I work at Sequoia Capital China, I look at tons of different founders. I look at how Sequoia China was able to make great investments in, for example, Kimi, Minimax, GLMs, and also Heijian, Manus, those and Unitree, all those great investments. I started to feel like I can understand more about how actual good business were made, and like how really good founders look like. So I think on that aspect, it's radically different from what I see at my daily job as a software engineer back then. But I also do think that type of knowledge are also like pretty important for me to operate Gradient as a founder. And also like one thing I generally benefits a lot is when I was venture capitalist in Sequoia China, I get to know a lot of good engineers. Some of them right now currently become our customers as of right now. So it also established a lot of good connections when I worked there. So that's another benefit. But like, most importantly, I just feel like at this current era of AI, since like most of our execution can actually be offloaded, can actually be automated. Like what actually eventually matters was the way that people, or like people put it, like your taste. So like your taste to real customer demand, the taste to how do you really understand the world's real challenges. And I think that's also something I get from my career as a venture capitalist. So yeah, so I consider myself to be a person with a lot of different skills. Maybe I'm not like the definite expert in one specific area, but I get to understand how things work in different aspects. So I can be, I think I'm doing pretty well into managing the system, managing the company in both a technical level as well as the go-to-market level, etc.
Yeah. And it's pretty rare to have like, I said like the full end of the spectrum. Usually, like either you go engineer and then like founder and then you go there, or you went
Yeah.
like venture capital and then you go founder. But you really did the whole tree,
I did a
which
whole trip. I'm a very curious person. Like I think one of the like most important characteristic of mine is just to want to explore. I'm a very like risk tolerant person, so I can tolerate like shifting my career path, like completely drop what I just did and starting a new career path like any given moment. So that generally leads me here, and I'm pretty like satisfied. I'm not having any regrets on anything. So
yeah.
that's just who I am.
This is cool. I wanted to dive then a bit more into like what gradient is, and especially like your vision, because I think I read somewhere that it's about generative collective intelligence. Can you like just articulate this for us? Like, what do you see when you say those words?
Yeah, so I mean, like general collective intelligence was more of the method to achieve the ultimate goal. So the ultimate goal of our company was always to lower the barrier for people to use AI and to own AI. I think like currently like when like OpenClaw came out, like people suddenly discovered that they are not able to afford like continuously running OpenClaw, like because just the token price is just too high. For example, if you want to use Opus 4.6 or GPT 5.4, it's gonna
Yeah,
cost you a lot. Like when they are constantly running those reflections, those cron jobs, and then people starting to realize, oh, actually, like AI has become so useful and so expensive that we as a human being like rely on it so much, but at the same time we don't actually have the power to use it how like as much as we want. There's a cost constraint to AI for the first time. Like before that, like people say like we just want to use the best models. We just want to use the cloud services, and then I think that's fine. So I think it become a more and more like imminent problem that token price are high, and as well as like training the ability to train models become like even more so concentrated in a few labs, because the capex you have to put into training models are like ridiculously high, that it basically become like cost prohibitive for any new labs to enter into the market. So we're starting to think what are some of the ways that we can mitigate the risk of having centralization, the risk of having the price of token become so high. So on inference level, on the serving level, we want to promote more of the personal sovereign AI type of stuff, meaning that if you don't want to leak your data towards some other company, the best way is for you to have your own open source models ways and host on your own hardware. So right now, I do think that the current world has become a world where everyone are involuntarily contribute their data towards some like large companies there. Like every time we're using cloud code max plans, we're
yeah,
basically telling people that you can train on my data.
yeah,
I'm currently solving those technical hard problems for you. And whatever you write, whatever like knowledge you put into this problem solving process actually becomes foundation for the next batch of model training. So like I think people should have the ability to choose an alternative way, which is using my own compute, like maintain my own data, don't let other people know what I'm trying to do, and also get access to the intelligence at any given moment and however they want, right? So even if they are on the airplane, they might be able also to get access to large language models. And also there are some areas in the world where large language models are not accessible to most of the people. Like say for instance in Hong Kong, like they aren't able to use GPTs and other
Yeah.
models. So they also like get like prohibited from using those models. Though local hosts are also very important. So, however, the major barrier for hosting a model is that the VRAMs are so large. You require so much VRAMs that most of your RTX 490s, even 490s, cannot afford. So that's the intuition of bringing more GPUs as well as Mac Minis and Mac Studios together into serve those models, even DGX Sparks, so that an enterprise and a personal, a household can maintain their own models. So like if you are using your own compute, the only price you pay is for your electricity as well as the upfront cost for buying those hardwares. But I think it brings sovereignty, brings cost effectiveness to whoever is using the model. And on the training side, I think we have come to a conclusion that pre-training are still the game of whoever raised $1 billion. I think pre-training requires you to spend so much money and time on data collections, data scraping, as well as the GPUs, which has to be located in one single data centers. However, I think post trainings are different animals. I think post training, most of the computes are actually spent on the rollout phase, which doesn't require it to be in one of the single data centers. And also, post training are more about data synthesis. I think it's less about how we are gonna scrape all the knowledge from of the humanity and fit it into the model. The knowledge is already in the model. We just need to build, for example, more environments to let the model explore. And that is also, I think, a lot of different labs, including us, can do. So, and by doing so, we actually can lower the cost for post training, lower the barriers for post training, because and also break the monopoly of the infra, so that more people can join this effort. So that's also echo with like collective intelligence, meaning that more and more people can join and provide compute, maybe writing code for post training, and I think that also provides a alternative for doing the alternative way of doing things compared to the traditional way of having one lab raising $1 billion and then do it all in house. So I think all what we do through like Parallax, the local serving framework, as well as Echo 2, which is the distributed reinforcement learning and training framework, are aiming at like lower the cost for training as well as serving. So in hope that we can bring a better world and an alternative for everyone who cares about AI and who is using AI, which I believe is going to be the 100% 7 billion person around the earth.
And you answer one of the question, which was the intuition between like the Echo series. But I think like you have a whole stack of a different element that are composing like the system that you're building, right? There's like the Echo series. There's like the parallax engine for like the distributed inference stuff. There's also the Latica that you're using.
Yeah.
Can you just like give me a summary of like each of them and like let me know if you have another one in preparation here?
Yeah, I think you basically cover some of the main component that we currently have. So for parallax is decomposing the model weights by layers and then use pipeline parallel to allocate that layers into some specific hardware that was memory constrained so that you don't assign all the model weights in that compute, but you rather assign a few layers on that compute and then it's sort of like a pipeline where the first machine like host like the 1s to 10s layer, the second machine hosts the 11s to 20s layer, and it can run on a pipeline. Like so for this type of serving, we actually need to connect two of the CPUs or two of the GPUs together in order for the whole pipeline of one token output to be in order for one token to be actually outputted from the system. So there should be some kind of interconnectivity module that need to be built in order for example, like your Mac Mini as well as my Mac Mini in my home to be able to connect together, so that we can establish a kind of like a global serving network. But even if like we are not like in different the compute are in different regions, say for instance you have a few compute locally at your home, how do we connect if the two computes are connected into the same Wi-Fi network, how do they connect together? So Dalika was born firstly out of this demand of connecting arbitrary different compute around the world, whether they are sitting behind the NAT or not. So sometimes, like if I directly want to connect to your network, it doesn't work because you are sitting behind an NAT. You probably not having a static IP addresses. Most of the household doesn't. So Dalika was built for this NAT traversal or just connect two different arbitrary GPUs across the world. And later, when we develop Echo, we found a problem that, say for instance, we have 10 different H200s around the world. And reinforcement learning are a process which is iteratively improve the model. We do a serving batch, and then we're using those results as the fuel for the next training run. And after the next training run, we redistribute the newest model weights to a lot of GPUs around the world to do another batch of serving and rollouts. So that requires we to very efficiently redistribute the model weights to GPUs who might locate at the other continent of the world. So one of the intuition was to have a P2P network, like before, like in like I think in the like 20 years ago, people are already discovering this P2P network to redistribute the file systems to everyone around in the world. So I think model weights can also be very efficiently redistributed in a P2P network, just similar to how like a lot of blockchain networks are operating. So later then Latika also infused this P2P content delivery network type of functionality in terms of every time our training swarm actually get a new version of model, Latika actually most efficiently have a multi-layered content distribution approach, which let the models get to all the sync across the network in the most efficient manner. So that also become the core components of Echo 2. And Echo 2 was just this fully asynchronized distributed rollout engine, which can enable distributed training, but do a regular think of all the rollout results and then do another round of training. So three components have to be worked together in order for the whole, what we think is sort of like the open intelligence stack to work, meaning that every GPUs in the world can do part of the rollout, while every other GPUs, some GPUs can do the training. So eventually the world become a supercomputer where every GPU
This is
was
so
put
cool,
in.
man. This is
Yeah.
so cool. And yeah, I wanted to ask this later on, but since we already touched upon it was very interesting to look at the peer-to-peer like broadcast system that you guys have in the paper. Can you just like walk us through like the difference with like the kind of star system versus like the peer-to-peer and why it's even needed in Echo, but like just generally speaking when you're dealing with like distributed GPU like that.
So I think for that specific question, we actually have to consult some of our expert into in designing the peer-to-peer delivery system. What I can see is that before the P2P system was used in redistributing model weights, it was actually very popular in China to use P2P systems to deliver video content. By say for instance, if you look at TikTok videos, most of the TikTok videos in China currently, or a great portion of it, is not delivered through TikTok's centralized CDN networks or centralized service. They're actually delivered by maybe some of your neighbors or some of the poorly maintained CPU centers in some of the like random places. So
Yeah.
those storage servers and CPU servers actually become the cache server for redistributed a great portion of TikTok's content. If we look at like video streaming area, which is also what I've been using to work for like in 2017 to 2019, the cost of doing content delivery, live streaming content delivery are just so high, so that people have to find a way to lower the cost. Like on the last generation, the most of the IT budget was spent on EC2, spent on CDNs. Right now it's tokens, right? But for last cycle, people are finding ways to use P2P networks to redistribute content. And
Right.
TikTok are also exploring this way of redistributed content using a peer-to-peer network, your computers, my like small NAS servers type of thing. They have been exploring from like 2017. And I think by now it actually become an industry that was actually functional. So I think model-based redistribution, we just sort of like copy the idea of doing the P2P content delivery networks, but apply it to the model-based redistribution
Yeah.
use cases.
Well, I find it very clever because it does like it does reduce the cost, but also like reduce the time it takes for everything to be
Yeah,
distributed properly, which
yeah.
was very nice. Um,
And also, I want to add that, like in reinforcement learning, there's a concept called staleness, which, like if you are always rolling out on the very like
yeah,
old generation of models, you get a lot of staleness, and the model actually cannot be trained very well. So, so for if we can redistribute the model weights in a very efficient manner to all the nodes out there, then we are dealing with less staleness,
true,
so and the
exactly.
training run are more stable.
Yeah, it's true here. And then you can like increase the throughput, and there's less waste with the rollouts.
Yeah,
But this is a very interesting element because while I was reading Echo one, I really thought that you guys will lean more, even more on the fully distributed asynchronous kind of situation. But in Echo two, you actually went centralized in learning, and you took the rollout phase kind of out, and you made it in more detail. Can you explain to us a bit like the intuition and like where does the shift happen, and what did you see in between Echo 1 and Echo 2?
yeah. So I do think we always maintain this idea of become like be very practical into what we're building. So we want our system built to be actually useful, to actually reduce the cost, to actually provide stableness in terms of reinforcement learning process. So I always believe that like on the training side, on the model weights update side, we should deal with very reliable GPUs out there. Like we should like I still think remains a huge challenges for like the for pre-training as well as the training phase in RL to be fully distributed. I think it
Right.
requires so much like data synchronization and like running it on the public internet is just not feasible at this point. So our ultimate goal was to provide a better service, a cheaper service for researchers, for enterprises. So we're sort of like dealing with in a more practical manner in terms of even if we still need the training round training phase to be centralized, is it possible that we first decouple training and serving, let the serving run on all the GPUs across the world, and then kind of reduce the need for putting every GPUs in one single data center, but
True.
because that's only like a few companies can afford. If you if you do the coupling for training and serving already, then you can already like eliminate the barrier for having so much compute within a single data center. The training side doesn't actually require so much GPU to be co-located because like most of the compute are in RL are spent on the rollout phase. So it already was a pretty, I would say, decentralized network, even if we just decouple the training and serving part. So I think that's the general intuition. And I think we're pretty confident that doing it in the distributed fashion can actually provide better efficiency as well cost effectiveness for our RL compared to if we do it in the centralized data centers.
Yeah, it's funny you say that because like this way of thinking about like how can we make it even more efficient. I really like when it's not just theoretical and then you actually look at the price of stuff and you're like, wow, we're spending like most of our time here, which is, I don't know if like this was an inspiration or anything. It reminded me a lot of the flash attention paper. Because like you said in the paper, like roughly 80% of RL wall clock time is spent on rollout generation. So only inference, only forward passes. And then this is embarrassingly parallel and latency tolerant. And in the flash attention paper, it's completely different. But like when you look at the attention calculation, you don't even need to make it like linearize or do any of this sort. You just need to make it use the GPU better. And if you just do that, you get massive gains. And then like we were able to like have more GPU utilization. And it was I had to do with like swapping the stuff in and out of a specific kind of memory. But that was where the issue was. In your specific case with the Echo 2, like any type of research that influenced like this type of thinking from your team?
You mean like when we were asking that question, are you asking that is there any other kind of intuition we can think about to better utilize GPUs?
Oh, well, that would be another question, but like here, anything like influence this type of thinking about like I'd say it like a more pragmatic type of research slash engineering architecture direction versus just like doing the thing for the sake of it.
So I do think we're sort of exploring if it's possible at the meantime finding out whether it is very useful or not at the same time. So I think like doing innovations in the machine learning systems actually requires you to have a first instinct as well as like you kind of verify your instinct and intuition on the go as you do more experiments. So at the very beginning, we don't know if that's even possible. We feel like it could be possible, but we don't know for at that point. At that time, we have the intuition of using distributed GPU that was underutilized, just similar to how CDNs are using underutilized bandwidth to lower the cost for content delivery. Should work. Like it should like provide some benefit. But what are some of the technical challenges we need to face? What are some of the technical barriers we need to face? Is it even possible to do things this way? We don't know for sure at that point. So we're developing the system on the go. We're testing out our hypothesis, and eventually we feel like that's something we're confident enough that we can say it's actually working. So I think that's the process of designing Echo 2.
Yeah, I really like this more like engineering, practically grounded type of research because like the gains are directly visible and it's hard to argue about them, right? I wanted to you have all this distributed kind of stack that is getting formed here with like the focus for LM fine tuning at the moment. Are you thinking of other type of model to train? Like, is it going to be only LM based, or are you also thinking about like the diffusion based system?
Yeah. So at the current stage, we're more focusing on the LM stage. But I think like currently like diffusion based the video generation type of models are also like they conduct extensive like run of RL to have a judger model to judge whether something I generated is physically accurate or is visually appealing, right? So for that, we're also gonna I think on the fundamental level, our system can also support that fine tuning. It's just that for the diffusion model to be able to enable fine tuning on our platform, we need to maybe like look at the details into how our system actually better integrate into that different paradigm of more modality of model fine tuning. So I would say like for this 2 to 3 months, we're gonna still focus on LMs, but afterwards we'll explore new areas.
Yeah, that makes sense. And are you also planning because I see that you're diving into the inference stack, the more environment like rollout stack. Are you also planning to dive into like the algorithmic part of the stack, or are you looking more to offer like whatever the algorithm are possible and like the user can choose?
Yeah. So our stance was more towards like there's a lot of lab where inventing new algorithms to train the models, right? There are a lot of innovations going around. So we as an infrastructure provider, we actually don't want. We have some algorithm experiment as well as research. However, we don't think our effort should be purely focused more on the algorithm side. what we need to do is to support the popular algorithms as they become popular, and then so researchers can actually benefit from that algorithms. Like right now, we see a lot of RL frameworks. We see Whirl, we see Slime, we see SkyRL, we see a lot of different RL platforms, RL open source repos, and they also all support some of the most popular RL algorithms there. So as an infrastructure provider, we also believe that we need to the thing we need to do is to support new algorithms at the as fast as possible, and without we as a research lab inventing all the algorithms there, because that requires so much capital to be spent there and so much time to be spent here.
Yeah, yeah. And talking about like the different part of the stack, the Echo 2 system rely on parallax, right? Um, how tightly is it coupled to
Yeah.
parallax? Could it technically be working with another inference engine?
So technically, we're currently using those two things together, but it's not actually tightly coupled together. So for Parallax, the design goal was more towards how do we do efficient pipeline parallel across different heterogeneous compute, whether it's Apple Silicon as well as NVIDIA GPUs. I think if eventually the future is that like every GPUs, whether it's strong or not strong, can participate in the RL process, then parallax become one of the very vital components in that world. However, like in the current world, I still think we're not there yet. So there are also a lot of good inference engines such as LLM, SGLang, and other inference engine that we can use, which are just as good and are iterating so fast. So so Apple 2 as a most of all a RL platform can work with all kind of serving engine under the hood. So I don't have like specific opinion of. Also, I don't think it's fundamentally correct if we're only stick to our stack, like without an open-mindedness to adopt other stacks the open source community offers.
Right, right. This makes a lot of sense. And I was very interested in Echo 2. I was very interested about the rollout plane, right? Are you planning on like drilling a bit more down into that specific section to make it, I don't know, to make more cost efficient to use on like consumer hardware to be able to create these rollout? Do you think there's
Yeah.
more optimization to be done here?
So first of all, I think there are always some kind of low-level system type of optimizations. We can like rewrite the kernels or whatever. Those are the hard work that for any kind of inference company they're doing day by day, right? For different models to optimize the serving efficiency for those models. But another thing I was pretty interested is in the like NV like FP4 type of serving the rollouts, so that we can use lower, like, because ultimately the limitations for the lower capability compute to be participate in the rollout phase is that they don't have so much memory, so much VRAMs to fit the
Right.
models into, and the serving is just like still a hard problem to do it very efficiently. So if we can use lower position in terms of rollout, while we maintain a relatively high position in terms of training, like there's gonna be some sacrifice in terms of the model that you actually train, because like you lose some data like through like low precision rollouts. But I do think in the future where we're able to and also the industry as a whole, we're able to define the paradigm of like, for example, like native like low precision training, native low precision rollout, and that's when I see a more of the consumer device as well as the enterprise like Edge 200 are able to participate more and more into the larger model size model training, because currently like the model size are getting like so much larger that even like sometimes Edge 200 becomes like less sufficient for the very large model to be doing efficiently rollout and train on those hardwares. So I think a lot of like open source labs, including DeepSeek, they are doing a lot of effort into kind of enabling this native low precision training to be able to fit more model weights into the lower capacity hardware that they can get their hands on. So I think people on the industry wise, the whole direction was to go towards that specific area, and we will aim for. We're also doing our internal research and also hope that other people can figure this out, so the whole industry can actually get there.
Okay, cool.
And also, like, there's another thing I want to mention. Like, it's gonna be pretty interesting, but not, I would say, figured out yet. It's like using like speculative decoding in the rollout phase. Like, speculative decoding was a practice where we instead of output one token, we output like few tokens, and then we have a small model which guide the generation of the large model. So the overall like rollout or serving speed can actually get a two times better speed compared to without speculative decoding. However, speculative decoding also involves some like information loss, and then the mismatch between what is basically off policy. So
Yes.
I think like how to get a like relatively on policy type of spec, but also enjoy the benefit of speculative decoding are also some of the research topics. I think that's going to be really interesting. But like those things I just mentioned are all contribute to the effectiveness or efficiency of RL, which still have a long way to go. I think eventually maybe fine tuning a or RLA like 100 billion parameter models are just not like so hard for a lot of people. So that is the future we want to push towards.
On that topic, like, what's your overall stance about like off policy RL for LM fine tuning? Like, do you
Yeah.
think it's like a worthwhile pursuit, or do you think like we should try our best to like, yeah, we can use it but not too much, but then steer back into like the on policy as much as possible?
Yeah. So I've talked to some of my friends in some of the core labs like Gemini, OpenAI, and also like the other large labs. And I think people are gradually shifting from like purely on policiness towards accepting some kind of off policiness. Like, for if you are a researcher working in the closed source lab, the frontier lab, you definitely don't want your info to mess up. You want everything to be on policy. You want like the purity in terms of how you do RL. However, like in some kind of like agentic RL like type of stuff, you have a so long of a trajectory, which if you wait for that one to complete, you actually waste so much compute, and it slows your iteration speed down. Like, say for instance, other lab can run like two round of iterations at like within like that's the 7 days, but you can only run one iterations, and the speed of iteration for your lab are going to be bottlenecked by how many experiments you will
Right.
run, because ultimately training a better foundation models right now is no like rocket science. It's just run more experiment and figure out what works and what doesn't. If your iteration speed was slower than other labs, you eventually lose your competency and your speed of deliver those models. So I think people they don't like off policiness, but they're gradually accepting this off
They're warming up.
policiness.
Yeah. They're
Yeah,
warming
because
up to it a bit. Yeah.
yes, and so like I still see a lot when I still meet a lot of researchers. They're talking about they just use on policiness. I think that's totally fine. But for eventually for the like enterprise RL, for RL on a massive scale by everyone around in the world, I think compute efficiency problem become a large problem. And then off policiness, if you are not aiming for like achieving AGI, then off policy become a must. I have a deep conviction into that.
Yeah, I say this because I was like recently reading like a paper that literally came out like in March, which like is from Harvard and Databricks. But like they basically were able to do the fine tuning with like 400 gradient step lag, which with
Oh,
GRPO is like absolutely doesn't work. But like what they done is that they made like another algorithm,
mhm.
optimal advantage based policy optimization with lag inference policy. And with this, they did a few trick inside, but they were able to get that lag without having to do the import sampling. So they removed that out of the picture, and it's
Okay.
basically like how's it called, like KL divergence based setup that is baked into the algorithm. But that's why I was so interested into this, because I feel like a lot of the gain is just to be able to use in some shape or form the staleness. If the staleness could be like longer, let's say it's still good at 30, 40, 50. I mean, like you would prioritize everything that is fresh, that is coming up, right? But if
Yeah,
like
yeah, yeah.
if the learner is waiting and he has nothing, and you can still use, let's say, one old 14 step before, without like messing up the whole learning. It is still, in my view, very interesting to see how this can be weaved in the whole situation.
Yeah, so imagine there are like just so much money, so many talents
Yeah.
devoting into figuring out RL, how to train it in a more stably. So I think all those questions are going to be solved very, very soon, to have more stable RL algorithms which can tolerate more staleness. Pretty optimistic about that.
Yeah. On the topic of staleness, also, like, how roughly do you think the very long, like, I mean, like, when you have long rollouts, you have all sorts of problem, right? Like, you have the credit assignment, like, you have all sort of problem. But like, how, like, a long rollout type of post training would fit within your paradigm with Echo 2 at the moment?
Yeah, so Echo 2 was a purely a synchronized RL framework, which means like for long rollouts, we don't wait. We accept a few steps of staleness. We also, I think, we did a calculation on the paper to see like what's the kind of the max staleness we can actually tolerate.
Yeah.
So speaking of that, we also like the staleness. When we talk about staleness, we also have to talk about how large was the model weights to be redistributed towards all the rollout engines out there. Because like if you are very large models, it typically requires transfer on the internet a few hundred gigabytes of data, or maybe in the future it's going to be even more. So it will become a bottleneck, right? But for the if you only like transfer the LoRa layers to the rollout engine, then it get much more efficient, meaning that you're basically just like one or two steps of staleness when you are like doing those rollouts. So I think so but P2P networks definitely solve some of those problems because we can like let 10 machines simultaneously stream different content to one machines. Like most of the time, like the machines download speed or faster than their upload speed. That's the case in most of the like households there. When you purchase the internet, you get like for example like one Gbps download, but if you do upload, it's not gonna be equivalent 1 Gbps. In most of the countries, it doesn't work like that way. So then 10 other peers can actually stream the content simultaneously to make you fully utilize your 1 Gbps download speed. But all the 10 like neighbors of your can like just need like 100 like megabits per second upload bandwidth. So yeah, I think for long back to the question, for very long rollout as well as for model weights transfer, we're trying to make first of all the engine tolerate to staleness, and we don't want to make the staleness as large as like 100 steps or 400 steps, but like I think like less than 10 steps of staleness are definitely doable, and it doesn't create so much of a problem here.
Yeah, and that was also my other question. Like, you got a 10x speed up on a 30B, like against like a firework and thinker, and it costs 10 times less. Like, how does this result hold as you increase the parameter count? Like, yeah, you're talking about like just like using LoRa and stuff. Like, does it mean that this should still hold as you go, I don't know, to 100B or something like that?
Yeah, so I do think going to 200B requires us to have. So the general answer is that it still hold as we go larger, but also requires us to have stronger like machines out there. So currently we're using
Yeah,
like
true.
H200 as of this current experiment. For this experiment, we can also use like H100, and I think the thesis will still hold. But if we're dealing with, for example, like 1 trillion parameter models, the 1 trillion parameter models actually take us so much of VRAMs in today's compute that H200 doesn't have a lot of room for KV cache as well as large batch type of rollout. So for that type of model, we first need to figure out how do we do low precision rollout and training, as well as we need to deal with, for example, B200, B300, and I think that's the more suitable type of machine that was suitable for it. That type of large models. But if we can use, for example, B200, B300, or even Vera Rubins in the future, then I think the overall conclusion will still hold for the cost effectiveness, because ultimately we're working with the idle or less reliable GPUs to do the rollout, which will ultimately also structurally provide a cost advantages compared to how you are dealing with very reliable and on-demand GPUs out there.
From Echo 1 to Echo 2, I see that like you kind of inverted the staleness element, and you kind of give it to the user to kind of decide, right? It's like now a knob that you can turn, like a staleness of 5, I'm good with this. What was the intuition here? And how would you deal, let's say, with like somebody that is turning out it to a 10 and then like has failing run? Like do you plan on like helping people out, like nudge into the right direction, or how were you thinking about it?
Yeah, so I do think like researchers all have different tastes. Some people like ultimately when I tell them we're dealing with staleness, they were telling we're not using staleness at all. We want to deal with like zero staleness and fully on policy. Some people are more tolerant. They want a cheaper RL. So I do think we leave the option towards whoever was using the product or the framework to decide, and we just do our best effort in whatever like staleness we did the best system for everyone, like but letting people decide.
Yeah, and I
Because
think
like also it's also a very dynamic
yeah,
landscape where like at the last like 2 months or people might like are super sensitive about whether they are fully on policy or not. But maybe like 5 months later, like people all kind of accept the off policiness because it gives them more cost benefit as well as iteration speed. So I think it also changes. So we don't want to make the decision for the industry,
yeah.
but rather let the user make their own decisions.
And I would assume it also depends on the type of RL they're actually doing, right? The type of like
Yeah,
task. Maybe
yeah,
some need to be much more on policy, otherwise it makes absolutely no sense. The other, it's more
yeah.
like a more general type of
Yes,
learning
yes.
that they're injecting. So I think it does make a sense that like you have this knob that the user could. I was just thinking about the S11 that just start to absolutely collapse, and I was like, if this happens, well, I'm playing around and I just wasted $1,000. I'll be like, maybe I should have had some guardrail here. But this is good. Well, thinking about this, right? Like if you were a startup and then you want to kind of just use Echo 2, let's say for a 7B, right? And you want to run it. What's the flow looking like? Like, do you need to provision a bunch of GPU? Like, how do you think about like, let's say a startup getting onboarded to that thing?
So at the current moment, we're currently developing our internal product, which utilize Echo 2 as the foundation framework. But we provision all the GPUs like for the enterprises. We provision the cheapest GPUs we can find across the globe to provide the absolute cheapest RL services to whoever want to use RL. So I think like majority like think about like Tinker. The intuition of Tinker is that like they handle this training so that like the researchers doesn't need to deal with managing the clusters out there. We think Echo 2 will be pretty much similar concept in terms of we handle all the GPU complexities that researchers don't have to do. They just design their algorithms, design their environment, they design what they're very good at and leave all the complexity to us. And so I think within like 1 or 2 months, you will actually see the platform actually be production ready, so people can actually try it out and train a 7 billion parameter models or so. And something like that.
That's pretty cool. Looking forward to this. And research wise, like, what's the next step? Like in this direction, which part of the stack are you thinking about the most?
Yeah, so first of all, we still need to increase the efficiency for the GPU efficiency for the whole stack. I still think there's gonna be a lot of things we need to work on, like including support more like multi-modality type of RL, more use cases. I think most of the time when you look at a lot of I've talked to some of the core contributors in some of the most popular RL frameworks, including Whirl, Slime, and a lot of the work that they do is to build a lot of peripheral modules that enables them to train this certain models, that certain type of models, that different type of RL, different type of Docker container, like environments or so. So on that front, I still think there's a lot need to be done into supporting all different kind of modalities as well as different environments to do RLs. And also in the future, we also well, like the ultimate goal was to lower the barrier for RL. So we also want to invest more of our times into think about what are the most scalable as well as the easy pipeline for a regular enterprise, not the frontier labs, to be able to use RL. And I think that's also something we in the future we will spend our time on. So the efficiency as well as the easiness of doing RL.
So thank you very much, Eric, for coming and chatting with me. That's it for today, folks. If you're interested in giving the gradient system a spin, check out the link in the description. And if you have any question, don't hesitate to shoot a comment. Have a great day.